Hello. Oh, there I am. Hi. So I should have read the bio actually because most of it isn't true anymore. But whatever. Blockchain. So yeah. Hi. My name's Aaron. I live in Austria. I'm not from there, but I live there. It's a nice country. It's beautiful. The thingy isn't working. There we go. Perfect. The title of the talk is this, but this is also a little bit of a lie. So if you came and you're like, this is exactly what I want to see, you'll see a tiny bit of this, but most of the talk is about proof of work and kind of what it is, why it is, and kind of are there alternatives. I'll talk a bit about the tech stack that we're using at our farm. But it's mostly about that. So you still have a chance to run to a different room if you don't care about that stuff. So being a miner, you kind of get hated from a lot of different sides. I also started the talk with a meme, which is either a really horrible sign or a really good sign. I have been gaming for most of my life. I think I got my first Nintendo when I was like 5 or 6. I love like all of the things, the Mario, the Street Fighter. I actually had bite marks in my video game controllers from Street Fighter. I might have anger problems. But gamers kind of hate miners for some pretty good reasons. I completely understand where they're coming from here because it's really, really ridiculous right now. If you just want to build a decent system, we're kind of like, and we're taking all the things. But I actually don't really feel that bad at all. So the other group of people that hates us is environmentalists. And I really feel for this side because this is me as a child. I was born an environmentalist. I hug trees. I love it. But like, really, they're completely right. It's screwed how much electricity we're using. Like, Bitcoin uses something like between Ecuador and Nigeria for the amount of electricity that it's consuming. And what I want to take a look at kind of is, I didn't really understand why this was happening. I did some research to kind of figure out why. I want to go into kind of why we do it. Why is proof of work necessary? I want to talk about kind of what mining actually is. So some examples of what a block is actually made of and these types of things. I'll try to do a demo. I don't know if that's going to so demo. And then I'll talk a little bit about alternatives to proof of work. Like, for example, proof of stake is the one that's talked about the most, and kind of what those are. And yeah. So before I do any of that stuff, I want to talk quickly about who I am. That's me on Twitter. I pretty much just retweet people. And I used to complain a lot about public transportation apps in Austria. But now I just mostly retweet people. When I'm not doing the mining stuff, I'm doing Elixir web development, some Ruby, some Golang, JavaScript when I have to. I'm managing I don't know what the size is comparatively to other things. Compared to something like Bitmain, it's very, very, very small. But yeah, so it's small or medium, a mining farm that I'm managing. I've been managing that for maybe close to a year now. And I'm moving kind of into building applications that make the blockchain more accessible to people. So web applications that can be built on top of these complicated infrastructure that's being built. So why do we mine? First, I unfortunately have to do kind of a quick intro into, this is the blockchain section, so everyone probably understands all this, but let's make sure everyone's on the same page. I'm going to use Bitcoin as an example just because it's the most ubiquitous, and a lot of the other proof of work related projects have used Bitcoin kind of as a basis. And so what the blockchain is at its base is a chain of blocks. It's actually, so the thing you'll see be thrown around the most is that it is an immutable distributed ledger. So let's kind of break that down into making it a little bit more digestible. What is a ledger? A ledger is a bunch of transactions that are recorded. There's the outputs. There's the inputs from the original account. So I'm going to send you money. You will see the money be taken out of my account, and then the money goes to your account. That will be an output. So it's a record of money traveling out of one place and into another place. It's distributed. So normally, these ledgers work. If we're using Visa, we're using our bank card. A bank is generally the central place where this ledger is held. So I try and move money around. I can always put those transactions through the bank, and then the bank can decide whether I have that money in my account to even spend, and then can send the transaction. So being distributed means there's a lot of attack surfaces for everyone has their own copy of the ledger, so there needs to be things put in place to block everyone from spending money that they don't have. And it's also distributed via nodes, servers that are running on different servers and places. It's immutable. It can't be changed. So this ledger is, every Bitcoin node has the complete blockchain. Every full node has a complete blockchain saved. And if each block in succession references the previous block, so if I go back in time and I change something, then that signature that's being referred to changes, and everything after that changes. So you can't just change one single thing inside of it. A block itself is it's pretty much just some metadata, and then a list of transactions going in and out of accounts. So it's in binary serialized. We'll talk about a bit later about kind of what's in the block header, but a block is really just transactions and then a little bit of information. For example, the reference back to the block before it. A full node is a server that is running somewhere that runs the Bitcoin daemon, which is just a piece of software that downloads the whole blockchain. The full node has a few responsibilities, being it contains the whole blockchain. So every full node has the whole blockchain saved on it. If I use a wallet and I send a transaction, the node that I'm using, my wallet, acts as a node, possibly two. The node takes that transaction. It verifies some things that it can verify about it. If the transaction makes sense, if the output is greater than the input, that's bad. So it goes through and it does some first checks, and then it takes the transaction and it pushes them out to the rest of the network if the transaction looks good. A miner is a special kind of node that looks in these transaction pools that the full nodes have. It grabs transactions out of them, it forms blocks out of it, and then it does the proof of work to try and validate the transactions. And then once it creates a block that's valid, it sends it out to the rest of the nodes, and then they propagate it through the rest of the system. So you have a block, get another block, it refers to the next block. This keeps happening. We have our chain of blocks that I had talked about earlier. If someone tries to change just one of these blocks, then that reference, boo, and then boo, everything explodes. So you can't change the past. Bitcoin D, I guess, uses a lot of memory. But Bitcoin D is just something that you can download and then run on your server. You can run it on any kind of VPS if you have enough disk space, which is 120 gigabytes the last time I looked. And I guess more than 2 gigabytes of RAM. The way that the node propagates, so this is very, very simplified. You send a transaction, a node picks it up, it sends it to its closest neighbors. These nodes are constantly asking other nodes for other nodes in the system. When you first start up a node, it looks at a DNS seed. So there's a few DNS servers around that will return a list of kind of base nodes or nodes that they know about. So if I just start something up and it doesn't know anything about the world, it can say, hey, DNS server, are there any nodes? And then it says, here are some IP addresses. And it says, OK. And then it starts trading back, hey, node, I exist. Give me your blockchain. Give me your friends. Tell your friends about me. And then those things go on. So you send it a transaction. It sends it to its nearest neighbors. Its nearest neighbors send the transaction to their nearest neighbors, and eventually the whole world of nodes has your transaction. It goes into a transaction pool, and then the miners will later pull from that. So what is the problem that proof of work is trying to solve? For example, so I'll give kind of a scenario without proof of work. So I want to buy a bunch of squirrel pelts, and I want to pay with it with Bitcoin, because I want to make some sort of a squirrel pelt jacket. So in a world without proof of work, blocks are created. They keep being created. And then our transaction goes out. I send 100 Bitcoin for some squirrel pelts. And it's on this block that this transaction gets pulled in and mined. So the blockchain keeps going further. Yeah, we have more blocks, more transactions. Great, great. You send me the squirrel pelts. I have them. I start to construct my jacket. More blocks. So at this point, I have my jacket started being constructed. I start creating my own version of the blockchain, where it doesn't have the transaction where I sent you 100 Bitcoin. It has a transaction where I send myself 100 Bitcoin. So I have this new fork of the blockchain, and I just build this. Keep building it out as quickly as possible. And then I start to buy a bunch of servers around the world. I start putting my servers. Servers are pretty cheap, thousands of servers. I put them everywhere in the world. Yay. My servers are propagating this blockchain that's longer than the original blockchain that has my 100 sent to myself and not my 100 for the squirrel pelts. So the way that this works is the blockchain is constantly forking. So if I find a block and someone else finds a block at the same time, they both go to the network, and the network is kind of split. Half of the network thinks that my blockchain that I send is the right one, and the other half thinks that the other blockchain is it, or some fraction of that. So what happens is, what the miners do is the miners are making a bet. Every fork ends up being a kind of gamble. So what the miners do is they say, I believe that the longest chain is the chain that is the truth. Because if they bet on the longest chain, they're more likely to win in the end. And then all of the blocks that they have mined in between will be considered good. If they go with the shortest block and it doesn't win, then all of the mines that they blocked all the blocks that they mined just disappear into the ether. So the blockchain would go with the longest one. I would double spend, essentially. You would never receive the money, the 100 Bitcoin, and I would get all of my squirrel pelts anyway. I'd build my jacket, and then we'd move on. So here is the world with proof of work. I would send you the money, and you would send. I would send you the money, and then you would wait a little bit to send your squirrel pelts. In this world, I don't have 51% or more percent of the hashing power of the whole network. Say I have 20% of the hashing power, which is quite a bit. For Bitcoin, it would take, I think, billions of dollars to get more than 51% of the hashing rate. So say I have like 20% of the hashing rate. The regular chain goes on and on. Every 10 minutes, a new block, on average, a new block is created. So 10 minutes go by, we both mine a block. Great, cool, lucky me. 10 more minutes go by, the main chain mines a block, but my chain doesn't. 10 minutes more go by, we both get one, more on your side, more on the side of the whole network. Yay. In the end, I can never catch up because I'm having to do this proof of work with only a percentage of the hash rate. So in the end, the winner is the longest chain. I don't get to double spend. But I wasted a lot of hashing power in the meantime. So I spent a lot of money to try and catch up, and I got absolutely nothing in the end. So this 51% attacks are a real thing. I think even today there was a 51% attack on Bitcoin Gold, which is a smaller cap coin. I think they stole millions and millions of dollars. What is it? What's the one with Pornhub? Not VeChain. Which one is it? Verge. Verge just, I think now in the last 2 months have been hacked twice with a bug in their code that allowed people to double spend and do 51% attacks. So it's very unlikely with Bitcoin because of the amount of money you'd have to invest to actually do it, but it's happening in the real world. So there's a downside to proof of work. It sometimes doesn't even work. So how do we actually do mining? What is mining? And to look at what mining actually is, we should look kind of at what is inside of a block. And as I said earlier, a block is just some meta information, some metadata inside of a block header, and it's a list of transactions. A transaction, if you go to a block explorer, a transaction looks like this. There is a input coming in from a Bitcoin address. Or sorry, you have an input coming in, it's a transaction ID. When this transaction is being validated, it looks back at that transaction and sees what the outputs of it is to see if those are even spendable. So you have a transaction ID, and then you have an output or multiple outputs depending on how you're sending your money. So if I am buying something for 2 Bitcoin and I only have a transaction that has 8 Bitcoin, or sorry, 10 Bitcoin is probably a better example, I can't split up the previous transaction, so I have to send 2 Bitcoin to you and 8 back to myself. So you will see, if you're looking at transactions, a lot of time you will see kind of change transactions inside of the blockchain explorer. So a transaction is just inputs and outputs. There's also a special kind of transaction called a coin-based transaction. Each time a miner creates a block, the first transaction that they put into it is called a coin-based transaction. It's generally to the miner's wallet address, and it is the block reward. So for example, Bitcoin, every time a miner actually successfully mines a block right now, they receive 12.5 Bitcoin. So what I would do as a miner is I would create a coin-based transaction as the first transaction, put 12.5 Bitcoin on it, and then put my address, and then when that block gets mined, in the ledger it shows that I have received 12.5 Bitcoin. So this is always the first transaction inside of a block. The block header is it's serialized data that there's a version number, there's a hash of the previous block, that's what keeps the blockchain referencing behind and keeps it immutable. There's a Merkle root, we'll go into that next. Timestamp, which needs to be somewhat accurate. Bits, which is how you change the difficulty of mining. So if I want to slow down mining, I make it more difficult to. So we'll talk about that in a second too. And then the nonce is this, if you've heard people say that mining is a bunch of computers solving a cryptographic puzzle. The nonce is the answer, essentially, or the last part of the solution to solve that cryptographic problem. So a Merkle tree. A Merkle tree is a hash of hashes of hashes of hashes of hashes that become a hash in the end in kind of a tree form. So you take all of the transactions, you hash them, so you have a list of hashes, and then each of those hashes you hash together, and the hashes of those hashes you hash together, and then in the end you end up with a single hash. And this is interesting because you can verify if a transaction belonged inside of or existed inside of a block only by getting the path, so that transaction's hash, and then the Merkle path to the root. So I essentially have the Merkle root of that block. I have my transaction ID, and then someone can give me, in this example, the blue things. So all I need is the HL, which is what I was originally hashed with, then the thing that it was hashed at the next level, and then the thing was hashed at the next level, and then the next level, and then I have the Merkle root. So you can see that to calculate if this transaction actually was here without using the Merkle path, I would have to do all of these hashes, hash together a bunch of times, and say there's not however many this is. I don't know. What? What is that? 16? Say there's not 16 transactions, but there's 1,000 transactions. It adds up really fast. So the Merkle root is wonderful. The bits. So bits it's a representation of how difficult it is to mine a block at this point. So the more hash power so one of Bitcoin's or a lot of these cryptocurrencies' goals is that they only want to release a certain amount of currency per X amount of time. So with Bitcoin, the block time is 10 minutes. They want it so a block is found only every 10 minutes. With Ethereum, it's 15 seconds, and you get 3 Ethereum. You used to get 5, and now you get 3. And then other ones have different times. There's one that I've been mining called Amoveo that is 10 minutes, and you get 1 Veo. So it changes. And the way that if you keep getting more hashing power coming in, more people are trying to solve this problem. It happens faster. So you need to adjust the difficulty to make it stay at whatever that threshold that you wanted it to be at. So the bit says what the difficulty was at this time, and it also shows if the solution to this cryptographic puzzle is valid. And we'll look at that in a second. So also, if you take the original, so do we actually have? Yeah, we do. So here is actually a block explorer showing the difficulty. Maybe I do this guy. So this 43 EC9 or 9A, A9 is the number, and this 17 is in hex for the significant digits after it. So this means 34 zeros after 43E blah blah blah. And this hex number is the number that when you hash the nonce, which is this guy, whoop, if you hash the nonce together with the block header, you should have a number that's lower than 43EC9A9 with 34 zeros after it in hex. You can see that this number is actually this number. This is a difficulty as of, I think, maybe 30 blocks ago in Bitcoin's blockchain. So when I hash these numbers together, I get a 32-byte number that needs to be lower when I convert it to decimal, or actually in hex works as well. I'm really good at these things. It needs to be lower than this number. And that's the cryptographic problem. So the nonce is the number that you're combining with the block header to create this number. So we have the header up here. It combines some hashes of the version, the previous block hash, the Merkle root, the time, the difficulty. We know all of those things. We know those. We're given those. We have all the transactions in the block that we're creating. Great. The only number that we don't know is the nonce. So we're trying to hash all of these things together with random numbers that we're trying to figure out, and then in the end up with a number that is less than that number that we looked at a second ago. So we just need the nonce. So you take the header, that's the nonce that you just created. You picked a random number, combined with the other things. You do a SHA-256 hash on it twice, and then you end up with a number. So the deal here is what people often say is you want a number with a certain amount of zeros in the beginning of it. That kind of works. That's kind of a larger thing, but the deal is that if I want one more zero here, then it's exponentially harder to find the answer when you don't necessarily need an exponentially harder solution. If you were only a little bit faster last time, you could probably just lower the difficulty by a little bit for the next period of time. So I've created this block. The nonce creates the hash that I was looking for. Great. I send it to all the nodes I know. I get all the things that I want. The blockchain, all of the miners say, all of the nodes say this is the correct chain. Great. But also, again, it could fork. I could get one of these purple things happening, and then the main chain keeps going. So eventually, the thing that I just mined could be rejected by everyone. and that's called an orphan block when that happens, and it sucks. So we're going to try, I'm going to try and do a demo. We're going to build a very, 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 very simple blockchain that is completely useless, but it kind of shows maybe proof of concept of what this is. I'm going to use Ruby because I like it. I think it's easy to read, and I'm going to talk about this at a Ruby conference soon, so it just translates pretty well. Our blockchain is just going to be 3 parts. We're going to have a blockchain itself. The blockchain is responsible for changing the difficulty and holding the blocks of the blockchain. All our block has is the block height, the difficulty, the previous block hash, the nonce, and a timestamp. And then a miner is just something that does the actual proof of work, and then we can add the block to the blockchain after the miner creates it. We don't have transactions. It's one thing that makes our blockchain that we're creating right now completely useless. But I think that if I was making Merkle trees and things, that it would take away from the point of proof of work. So this is what the code looks like. You take a difficulty originally in the beginning. The difficulty is stored, or it just picks a very, very easy difficulty. You can then later set the difficulty to something else if you want to. You can add a block, which just essentially adds blocks to an internal array, or like a block or a block pool, I guess. To get the next block template for the miner, you can say, hey, look at the last block. Cool, perfect. And then we can check if the block is valid by seeing if the difficulty is correct, and seeing if the block itself says it's valid. So a block has those things I talked about. It references the previous block hash. It sets a height based on the last block's height. The difficulty is whatever you set it to. It comes from the blockchain. And then you can get a hash of the current block to give to the blockchain with this hash, which just does a double SHA-256 like you saw in the last code. And then the header is just a combination of the previous block hash, the diff, the timestamp, and then we'll add a nonce to it. The miner takes a blockchain, and then when you tell it to mine the block, it guesses. It starts with 0, and then it starts incrementing the nonce by 1. It's not picking random numbers. It would be bad if I had lots of these things doing this, because all of the miners would be picking the same nonce over and over again. So this is the slowest and dumbest miner that you will ever see. It adds the nonce, and then it checks if the nonce is valid by hashing the things together, which you could see here, valid. And then if it's valid, then it returns it. There's also kind of a helper method here that we can mine 100 blocks if we wanted to. It just keeps going through and remining and remining. Yeah, so yay. I don't think I've ever done a demo at a conference before. So this is going to be fun. That just happened. So I'll make it bigger. OK. So we're going to create a blockchain first. So I can't actually see what I'm doing. I'm just going to go back in history. You can see why I don't do this very often. So we have a blockchain. The blockchain has this difficulty. This is a very, very big number, so it's pretty easy to beat. And then there's an empty block array there. Then we can go, what? Miner equals there. So we're creating a new miner by adding the blockchain to it. Yay, we have our first crypto miner. Time is not going great for me here. And then what are we going to do? We're going to miner.mineBlock. Probably should spell things right. Yay! So we have our first block. You can see that the nonce is 39. So that means that it had to try 39 numbers before it came up with the answer. Let's try it. Let's add this. We can do bc.add block b. Yay, we have a block in our blockchain. Now we can mine a block again. You can see that now we actually have the previous block hash, and it starts with 2 zeros. This is the difficulty, if you're talking in zeros, is 2 zeros for this guy. The block, it went up to 31 this time. So let's actually set the difficulty to something a bit harder. Actually, here, let's do this. So this is just me cheating and making a hash or a hex number bigger. So this is an 000 with 60 Fs after it. So we're setting a new difficulty, and then we're going to try and mine the block. And you can see now the nonce is at 12,000. Try again, it's at 29,000. We can go crazier than that. And these are going to kind of exponentially be getting slower. So that's 487. So that's the whole point. When you change the difficulty, it ends up taking longer. You have to try in more random numbers to try and guess what it is. And you can also see, if we do it again, that our block hash from the previous one is going to have more zeros at the beginning of it, if it ever happens. Sometime. Any questions? This is the fun part of this demo. Yeah. So, oh, there we go. So we got up to 2 million. So Ruby's also slow, and I did not make this a very performant code either. And then we can, I'm just doing this again, and we're going to, nothing's working right. OK, perfect. Yay. We're miners now. OK, so just really briefly, I'm cutting into the Q&A time. So the farm that I'm working on, it's in Austria. We have 165 rigs with 5 to 6 cards on each. Prime Crypto is the company that I'm working for. There's like a collection of startups. Prime Crypto is one of them. Here is inside the container. All of these things are video cards, and here are bare motherboards that are connected to them. It's really nice, and it's really homey there. We should probably put up some kind of a picture or something. Here's a closer blurry picture. I only have blurry pictures of this, by the way. Sorry, if you're far back, maybe you don't notice. There's some cards up front. Here is a gamer's paradise, I guess. It does this when it's dark. The noise, there was no sound. It's supposed to make a fan sound. There we go. That's what it sounds like. It's loud sound. It's not as bad as like the other ones, but yeah, great. So the tech stack that we're using is for the hardware. It's commodity motherboards. There's some Asus gaming motherboards. We only use NVIDIA GTX 1060s right now. There's about 165 rigs. There's about 5 to 6 cards per rig, so close to 1,000 cards. Because we overclocked, the hardware got kind of pushed to its limits, and the rigs really hate everyone, so they just disappear sometimes. So I named the rigs after a combination of Lord of the Rings characters and Zelda characters. So we have Puddingfoot. And this helps. It actually helps a lot, because if one rig keeps disappearing quite often, it's really like, oh, Faramir's gone, or that's actually a shitty rig. That's why I use that name. Hate that rig. So they actually, like, the hardware just goes nuts and doesn't work how it's supposed to work at all. And the farm isn't anywhere near where I work or where I live, so it's like kind of sucks to take a train for hours to be like, oh, let's restart the. So what's actually being installed today is a bunch of Raspberry Pis that are set up with relays to hard reset the rigs that become inaccessible. So that's fun new step. The software, there's one central server per container. It's just running Ubuntu. All of the rigs are hardware, like they're hard driveless. They all Pixie network boot. They download the operating system and then immediately start mining, which is pretty cool. If we want to bring a new rig, we just plug it in. They all share a root file system, so that's the downside. There's also a lot of network traffic because there's a lot of NFS traffic going on. I built some Ruby simple stuff to switch coins, so it's just a simple HTTP server that runs a Docker a Docker client that you send it an HTTP request, and then it kills a Docker container and starts up a new one with the important information, the wallet address, the mining pool address, those kinds of things, which coin it is. And so we could just like, oh, we want to completely switch to Electronium right now. We can just be like, mine Electronium, and it will start mining Electronium. Some Ruby, tons of Bash, Golang. I don't know if there's any Golang left anymore. Ansible is what I use to set up the servers and the original rigs. Docker is used because it's great for this mining thing, but I've been having some issues with Docker over NFS. A lot of the rigs not a lot, but a few, like maybe 3 of the rigs, Docker daemon won't start, which is awesome. I guess I was being sarcastic. We use different mining software. We built containers around them, ETH miner, XMR stack, CC miner, Claymore, other things. And then to do some of the monitoring, we use Grafana and Influx and MQTT. So the rigs all are sending messages constantly to this server that's running a MQTT server and InfluxDB and Grafana, which are also in Docker containers. I've kind of finally been like, OK, I guess I'll try and start using Docker. And I kind of went a little bit nuts with it. So that's a thing. If you want to talk about any of this stuff with me afterward, I'm super into it. So here's my rig. This is at my office. I get free electricity at my office. You can see that is one of the video cards. This is an external fan that is sandwiched in there, like it's actually forced in there. There's another video card, and there's another external fan sandwiched in there. I tried to get this in shittiest rigs on Reddit, and I didn't win. I only got 5 votes, but I think it's a pretty shitty rig. So we're going to talk now about alternatives to proof of work. Here are some. I don't think I talk about all of these. There's proof of stake, proof of burn. I actually don't talk about proof of time. I don't even know what that one is. I think it's a thing, though. Does anyone know what that is? You can come up after me and talk about it. So proof of stake. I'll try. Proof of stake. In proof of stake, instead of having this cryptographic problem that happens that makes it so things happen every 10 minutes, they have this idea. I think that this is with Cardano and possibly also with Ethereum. They have this idea of epochs, where I'm probably pronouncing that wrong. English is awesome. So you have an epoch, and it's some sort of a period of time, and this epoch is split into different voting stages or different voting times. So what happens is you take some kind of amount of coin. So say I have 100 Ethereum. I stake this coin. I put it in a special place, send it to a special address or something. It sits there, and with that staked Ethereum, I am then able to vote on who the next person to validate, the next node to validate the next block is. So the more money I stake, the more chance I have of being able to vote on the next person or the next node that is validating the block. So these times go by, we vote, great, things are voted on. There's the idea like of honest voting and dishonest voting, where if I hear 2 things from 2 people or 2 nodes, I trust it. If another one's lying, I don't trust that node anymore. Or if another node says something else, I don't trust that node. At some point, if you're a bad actor, you can have your stake. Love this animation. You can have your stake burned, which means that just you don't get it anymore. So less of an incentive, whereas proof of work, the incentive is you have to spend a lot of money on electricity. With proof of stake, you have to spend your stake gets burned if you're a bad player. So you don't want that to happen. That sucks. So proof of burn, I probably should have used the animation again. I'm sorry. Proof of burn is a situation where you take your coins and you send them to a burn address or to just like a random, I think with some implementations, you just can pick a random address and you send your coins to it. Depending on how much money or how many coins you burn, you get more of a chance of winning a lottery to be able to validate the next blocks, which I think most of the time sometimes there's a block reward, sometimes you just get transaction fees, whatever. The more you burn, the more you're likely to get in the future from these lotteries. So it makes also more sense to keep more currency in the system. So it's kind of interesting that way, where you're kind of waiting. You're like, oh, with proof of stake, you have to wait a little bit to make sure that your stuff gets validated, and then you can take your stake out. But with this, it feels like there's more, you want to keep your money in there more long term. So what's happening? Proof of identity. Proof of identity is, there's at least one project that I've seen where people have to become legal like notaries, which means you have to go and take a test, which takes a certain amount of time and effort. You have to pay money, I think. And then you get registered on this national, I don't know if this is US only, I don't know what the deal is, on this notary system that's an external database that that then some sort of an oracle in the system can say, hey, does this person actually exist? Does this person actually exist? And it's like, yeah, this is a real person. They are a notary. We have their identification. They spent time. So in this case, you are actually burning your reputation if you do bad things. And as this rich man said, that reputation is very important. But he also hates Bitcoin. So proof of capacity. This one I don't understand very well, but I think it's kind of cool. There's a coin called Burst Coin that does this. Essentially, you take hard drives and you preload them with solutions or something. This explanation is better than any I'm going to give you, even though it's still not very good. And then when new blocks are supposed to be minted, you can look through your solutions and then whatever. So you have to do this whole process of taking your storage and preceding it with a bunch of hashes, and then great. And this is great because another way of like using less electricity, you just have to buy a bunch of hard drives. There's some good videos on YouTube if you want to see me do that. If you want to see people actually setting up their giant hard drive arrays for Burstcoin, it's pretty interesting. And that's everything. So I don't know is the answer. We're spending a ton of electricity. I don't like it. I don't know what the future is. Yeah, I don't think it's proof of work. But yeah, now maybe you have more of an insight into those things. So thank you. Thank you.
Thank you, Aaron.
14 minutes. I'm over time. I'm almost leaned on this. That would have been.
No, but you have to still do some Q&A.
Okay, I'll do some Q&A.
Do we have any questions from the audience?
The answers to anything.
You get the microphone, sir.
Fuck.
Your mic is still on.
Yeah, I know. I heard it.
Do you automatically choose the coin you mine?
So right now, this is the kind of question I like. It's a great question. We right now, it's mostly like speculating. There's mastermind groups that people on the team are part of. People are kind of like looking for coins. Right now, since we don't have a lot of hashing power, it's mostly about making good bets. So right now, we just pick something, and then I decide, and then I say, hey, server, send this request to all of the rigs, and then it sends it. So it's fairly manual right now. But with the setup that we have, we can do like 100 different coins right now, maybe more, because we can hit, like, especially with CC Miner, there's so many algorithms that you can hit with it. In the future, we would like to do more have something that's like looking for profitability, and then an automatic coin switcher that can say, what is the most profitable right now, what makes the most sense, and then switch to that. But right now, we're still developing some of the core stuff, so.
One more question?
Hi. What do you think about the IOTA? Do you know the graph?
I wanted to talk about IOTA a little bit. I don't know what I think about it because pretty much everything that I hear is just drama about kind of everything in the space. There's a lot of drama. Supposedly, they don't like criticism very much, which is a really shitty thing to have as the core developer of something that's really, it sounds super awesome. Like, it sounds really cool to me. So the deal with IOTA is that instead of using a chain, they use a graph. It's called a DAG. It's actually a similar structure, I think, to what Ethereum uses to put all of these things in memory to make it so the ASIC miners, the things that like on Bitmain, all of the specialized Bitcoin miners that make it so we can't mine Bitcoin anymore with GPUs, they have this very memory-intense thing that they do before you start mining Ethereum that makes it so it doesn't really work with ASICs. They use a similar thing that's completely a tangent, but they use a graph that a node is created that is like a block, and this block has at least two, maybe just two nodes that are its neighbors. And when that block gets mined, or when that block gets created, you have to mine the two, or when a transaction gets created, you have to mine the two blocks next to it. So essentially, everyone is a miner. And I mean, this doesn't really do anything for electricity because maybe it does. Maybe I'm not understanding something correctly. But what it does do is it makes it so like transactions are really cheap. It makes it so like everyone is mining everything. Like and it makes transactions incredibly quick too. Like it's quick and it's cheap and everyone's a miner. But like I wanted to go into it and then I was like, actually this isn't an alternative really because it's still proof of work. And if I did, I would have had multiple slides for it, because I think it's a really cool project. You should look at it. But yeah, cool.
Well, thank you. And we have our next speaker in 10 minutes, which is Nicolas Karaniemi, and he will talk about JavaScript and self-deception and why TypeScript is not enough. Thank you, Aaron.